We are Group 3 for Spring 2018 Capstone Project. We did UCSF Block 33. We are CSB Construction, and now I'm going to give a quick overview into project personnel.
My name is Ben Capone, and I focused on site logistics.
My name is Christian Gutierrez, and I focused on the traffic study and scheduling.
My name is Carolina Lopez, and I worked on scheduling and BIM coordination.
My name is Sergio Montes. I was responsible for estimating and creating the bid model.
My name is Christian Rose, and I worked on estimating and BIM coordination. And now we'll talk about project overview.
The Block 33 project was for the UCSF school. It was a design build project with a budget of $237 million. It had 300,000 square feet, and it was a medical tower with 2 6-level wings. Now I'll pass it on to project consideration.
Some considerations for this project was location. Since it is in downtown San Francisco, the logistics was a little tight. This is also an active campus, and it has an active hospital next door. We also had to take into account the helicopter flight path that leads to the hospital. Here is a brief overview of the location of our project. We will now move it on to the structural concrete plans with Sergio.
The above ISO illustrates the 12-story tower with the 6-story mid-rises attached at the base. The building is again erected in the downtown San Francisco area and is adjacent to the university and an existing medical center. Using Revit's takeoff function, we were able to pull quantities from the BIM model, and using these quantities, we came up with a rough estimate for the building plans. And now to site logistics plan.
UCSF's Block 33 will be a complex and fast-paced design-build construction project in downtown San Francisco. Located on an active university in a very populated city and adjacent to a busy hospital, the project engineers from CSB will face a variety of construction and civil engineering issues during all phases of the project. Due to these facts, a well-organized and planned-out site logistics plan is of very high importance for the safety of pedestrians as well as the site workers. The following site logistics plan focused on material delivery and trucking routes, overall site flow, restricted airspace, crane selection, building erect plan, and concrete pour plan. This image is a screenshot of the overall site logistics plan. This plan was put together using Autodesk InfraWorks 360 BIM software and takes in all the various factors that were discussed in order to provide the smoothest site operation plan. This image is taken after the towers have been erected and cranes are not shown in order for clarity. Crane selection played a major role in this project, which will be touched on later. This is another screenshot of the logistics plan. This one highlights the laydown area and shows trucking routes. Materials, personnel, and other equipment and resources being trucked in will enter through the east gate located off Illinois Street and will exit in the southwest corner of the site. Materials entering by truck will proceed to the material laydown and staging area. They will be unloaded and proceeded south, eventually exiting out of the south exit. Due to the active hospital adjacent to the site, lane closures or traffic detours are not an option, as emergency ambulances are subject to operate on that 3rd Street. Also note the gray shaded area on the upper part of the screenshot. This area represents the emergency helivac airspace, and this airspace can absolutely not be obstructed. For this reason, crane selection had to be very carefully thought out. If that airspace is obstructed, it will pose a major safety hazard for both site workers and medical personnel. 3 types of cranes were considered. We considered tower cranes, mobile cranes, and luffing cranes. Due to the size of the site and the severity of the consequences, if placed in the wrong spot, we elected to use 2 cranes instead of 1. We decided to use 2 tracked mobile luffing cranes. These cranes, along with the pick plan that was thought up, contribute to the safest possible option while minimizing risk and cost. Tower cranes would obstruct the airspace and both cost too much and take too long to mob and demob. Therefore, they are not an option. Luffing cranes are able to stay out of the obstructed airspace, and with this building erection plan, the crane will move from north to south, erecting the separate towers as it goes south. By moving in this process, this will allow the crane to be out of the obstructed zone the fastest and again minimize the risk. The concrete pour plan operates in a similar fashion as the pick plan. The north tower will be poured first by using a truck-mounted pump, since it is only 4 stories tall. The next 2 towers will be poured by use of tower-mounted pumps. 3 tower-mounted pumps will be utilized and will provide sufficient coverage to reach all corners of the building. Concrete trucks will follow the material trucking routes and will be staged in the laydown area that are previously discussed.
Prior to any large-scale construction project, it is necessary that a traffic analysis be conducted to predict and prevent traffic flow analyses. This was especially important for our Block 33 project due to its close proximity to the University of San Francisco campus, the UCSF Bainoff Children's Hospital, AT&T Park, and the Warriors Chase Arena. Possible disruptions to emergency vehicles and access to hospitals was our main priority when we began our analysis of 16th Street and 3rd Street on the 33rd block of San Francisco. Our traffic analysis approach was to determine the level of service before and after construction. As defined by the Highway Capacity Manual, level of service is a qualitative measure that classifies a road from A to F depending on average vehicle delay. Our methodology for this approach was to determine the existing level of service of the current street configuration surrounding the project prior to construction. We then conducted a series of adjustments to the free flow speed of the street by taking into account number of parking spots, peak hour factor, and heavy vehicle factor. Once we determined the free flow speed after construction, we were able to determine a new level of service. From our research, we determined that the existing level of service prior to construction for both streets was C, or light congestion and backups on approaches. After we adjusted our base conditions to account for the increased traffic flow caused by our project, once it was fully functional, we concluded that our level of service for 16th Street was a level D and 3rd Street was a level F. This scenario would be catastrophic for emergency vehicles which would be disrupted due to traffic. Our recommendation to the San Francisco Public Works Department was to improve the existing road conditions to a level service A.
So now for estimating, the purpose of the estimate was to compare the material costs of a steel building versus the material costs of a concrete building. Using the created Revit model, we were able to model major elements and extract those model elements, provide quantities and unit costs to them in our cost data sheet to give us a total estimate. So for the steel we estimated around $30 million for a steel building, while for the concrete estimate, the total cost was around $12 million, which was significantly different in cost. So from a price perspective, we recommended to the UCSF owner that they should select a concrete building. And I'll pass it on to scheduling.
The schedule was created through the use of Revit and Primavera 6. We had set constraints for both the structural steel and structural concrete comparison. Both projects would begin on June 5th, 2018 and would follow a 5-day work week schedule with major holidays as non-work days. Both schedules also had identical foundation plans for an accurate representation of the erection of both buildings' materials. The structural steel had activities including mat foundation, slab on metal grade, erection of steel, plumbing, metal decking, and spraying of fireproofing. For our results, we found that the structural steel would be erect in January 11th, 2019 with a duration of 155 days. The structural concrete had the same foundation activities. In addition, we considered the formwork placement of vertical components, the formwork deck, set rebar, and install MEPs and pour decks. Our results were that the construction would end on August 7th, 2019 with a duration of 302 days. The concrete schedule was significantly longer than the steel, so for a structural concrete schedule would be better for the project and is recommended. We also conducted a single level schedule based on the image displayed. The construction would begin on October 8th and would be complete on May 1st, 2019. This is a duration of 148 days from framing to finishes of the entire floor. Our schedule was started with the fire rated corridor. Since this is a medical building, they were our number one priority, and then would move on into the non-fire rated areas of the building. We will now move on to BIM coordination. For BIM coordination, we used Navisworks to import all of the models provided and created a clash detection between the concrete and the multiple MEP trades. Displayed is a single major clash between the concrete and the waste plumbing pipe. This is significant because the plumbing pipe have to follow a specific slope in order to successfully function. So our proposed solution was placing a sleeve during the installation of the formwork in order to have a proper fitting with the pipe and the concrete. The contact of both the structural engineer and the civil engineer would be required to approve said solution. Our overall recommendation for the project between structural steel and structural concrete is for the UCSF school to go with structural concrete. Although the schedule was significantly longer, the price is too low for us to neglect, and we recommend going with the structural concrete. Thank you from CSB Construction.